Hello everyone, welcome to week 10 of Codivate Python class. For this week we're just going to do a bit of practice. We're going to review a lot of the concepts that we did before through a bunch of practice problems. For our first practice problem, we have to write a function. This function takes one parameter, a float temperature in degrees Celsius, and it was going to return the temperature in degrees Fahrenheit. So just as a note, the conversion from Celsius to Fahrenheit is that 1.8 times the temperature in degrees Celsius plus 32 is equal to the temperature in degrees Fahrenheit. Now would be a good time to pause the video, try to attempt it yourself, and resume when you're ready to review the solution. So this is a pretty simple function to write once we know the formula for conversion. In our example solution, we named our function C2F. Since we are going from Celsius to Fahrenheit, we have the def for the definition as usual, and we have parentheses, and inside we have a parameter, which is degrees Celsius. So we're just going to call it Celsius. We have a colon to start off our function, and inside our function, we're going to be just returning one value. This value is going to be 1.8 times whatever the inputted degrees Celsius is, plus 32, because this is how we go from Celsius to Fahrenheit. This is going to be returned by our function, and we can test it out through a couple of function calls. We can test it out with Celsius getting an argument of 0. C2F of 0, we would be returning 1.8 times 0, which is 0.0 plus 32, which would be 32.0. One thing to note is that all of this will have the 0.0 at the end because we are working with floats. 1.8 times anything will give us a float, and this float plus an integer would give us a float. Same thing, we could test it out with an argument of 100. C2F with an argument of 100. 1.8 times 100 plus 32, 180.0 plus 32, which gives us 212.0. Just to make sure that we did this correctly, we can look up an online temperature converter, plug these values in, and make sure that they have the same exact output. Our next problem is called increasing list. We have to write a function that takes a list as a parameter and returns true if all the numbers in the list are in increasing order. This means that every number is greater than or equal to the previous number in the list. However, if this is not the case, we'd have to return false. So true and false is a big hint that we're going to be returning a Boolean. Now would be a good time to pause the video and try it out yourself. Alright, let's take a look at one solution to this increasing list problem. Here we named our function isIncreasingList. We have our def for define, and our parameter is going to be one input list. What we're doing inside the function is returning this Boolean that checks if two things are equal. Well, let's try to make sense of this. We are checking if the sorted version of the input list is equal to the original input list. In the case that this is true, this means that the list is in increasing order. But why does this happen? Let's go back to the prompt. We want to make sure that we return true if the numbers are in increasing order. What sorted of input list is doing is it's creating a version of this list where it's in increasing order. So if that increasing order version is equal to the actual list, we know that the list is in increasing order. Because this is a Boolean that will return true if this is the case, these two are equal. Otherwise, it will return false. We can test this out with a couple of different lists. So we know that a sorted version of this would look like 1, 1, 2, 4, 4. And since those two lists are not equal, we'd return false. And a sorted version of this would look like 1, 1, 2, 2, 4, 5. And since those are equal to the current values of the list in the order, this would return true. That solution is a bit more efficient, but it's a little bit harder to understand, and it doesn't 100% model the problem where we're checking if each number is greater than or equal to the previous problem. So let's take a look at another solution to this one. This one is a bit more methodical and applies some of the concepts we learned about loops and conditionals. This is not the most efficient, but this one applies the model of the problem pretty well. We have the same function header as before, but instead we're going to be looping through the indices of the list. We start at 0, which is going to be the first index in the list, and we end at length of the input list minus 1. Usually we end at length of the input list. However, we're going to end at length of the input list minus 1 because we're comparing two values in the list at a time. So if we left it without the minus 1, at the end of the loop, we'd be comparing the last item with the item after that. But since there's no item after the last item, we can't do that. And we need to specify this minus 1 here. Inside the loop, we have our conditional. We check if the input list of the item after the current item is less than the input list of the current item. So what is this doing? This is checking. Is an item after the current item greater than the previous item? Or less than the previous item? It's the less than sign. So if this is less than this, as an example, if we were looping through the first part of the list, if this is less than this, we'd have to return false because this indicates that a value after the current value is less than it, and if that's the case, we know it's definitely not increasing. If that's the case, if that happens at any point in the list, we return false and we're done with the function. That's it. Because there's no possibility that if one part of the list is decreasing, another part would make it so that we could undo the decreasing part. That's not possible. If we make it through the entire list and there's no points where the list is decreasing, we know that it must be an increasing list, so we return true. Once again, we do these test examples here. We would be looping through this list. We are checking, is 1 less than 4? Since it is, we immediately return false and we exit this entire function. We don't keep going. As soon as you return something, we are done. In this one, what we do is check once again. If 1 is less than 1. Well, 1 is equal to 1, so we don't have to return false yet. Then we do is 2 less than 1. Well, nope, 2 is not less than 1, 2 is greater than 1. So we don't return false. Keep doing this, and at the end, we end up that we don't have to return false at any point. This means that it's not a list that has any point where it's decreasing, which makes it an increasing list, so we return true. Our next problem is called self-divisor. We have to write a function that takes an integer parameter and returns true if the parameter is divisible by each of its digits. For example, if we call this function on 128, we should get an output of true since 128 is divisible by 1, it is divisible by 2, and it is divisible by 8. These are all of its digits. One special case to consider is that if at any point and we're looping through the number, we get that one of the digits is equal to 0. Because we can't divide by 0, so if you were to try to test if the number is divisible by 0, you would get an error. So if at any point we see that one of the digits is equal to 0, we must return false since it's no longer a self-divisor. Now would be a good time to pause the video, try to do it yourself, and return when you're ready to check the solution. Alright, let's go. The first one involves creating a string called digits. And inside our function we have a function header. Let's just go over that before. We have def is self-divisor, and it's going to be taking in a parameter n, which will be the number we're checking if it's a self-divisor or not. We have a string we're creating here called digits, and it's getting a string version of n. Why are we making it a string? Well, the reason is because we can loop through strings, but we can't loop through integers. And we want to loop through each letter in the string and we want to make some checks. We want to check if it's equal to 0, if one of the letters or digits is equal to 0, and we also want to check if it's divisible. For example, if the integer version of this digit is equal to 0, once again, remember, digit will be a letter of this string version of the number. So if an integer version of the current digit is equal to 0, that means we have a 0 in our number, and we know to immediately return false because we can't divide by 0. Otherwise, you're going to be checking if n modulus int digit is not equal to 0. What is this checking? Let's back up a little bit. N is the original number, modulus, and not equals 0 means that we're checking if something is not divisible. Digit, int digit is just the current digit. So let's try to read this all together. If the number is not divisible by the current digit, then we return false. And that's true. We want to make sure it's divisible by all the digits. If it's not divisible by any one of the digits, we have to immediately return false, and we're done. However, if we make it through this entire for loop and we never return false, that means we know that that all the digits are divisible by the number. The number is divisible by all the digits. In that case, we return true. You can kind of think of this for loop as a strainer. It's straining out all the cases where it's false and leaving us with only the cases where it's true. And if it gets strained out, we just return false. Once again, always a good idea to test our code. We know that 64 is not a self-divisor since it's not divisible by 6. We know 128 is a self-divisor. That was our original example. We know 100 is not a self-divisor because it has these zeros in it. One thing to note is that since we're using return false twice here in two separate conditions, we can just combine these conditions with an AND, but it's important that we have this int digit equal 0 to be our first condition so that short circuit evaluation can work. If you're not sure and you need a refresher on short circuit evaluation, you can go back to one of our previous videos on booleans. So we need this to be first because we don't want to be checking if it's divisible and find out that it's equal to 0 later. We want to make sure it's not equal to 0 before we actually do division with it. So the solution that we just went over is very simple to use in Python, but not easy to apply into other languages. So we're going to go over a solution that also works in other languages. We have a very similar method header, or function header here, def self-divisor, and this time we're going to be using an approach that we've used before when going through digits in a number. What we're doing is basically looking at the last digit using modulus 10, and we're doing the same condition checks that we did as before here. It's just that since we are never converting it to a string, we don't need to cast these back as integers here. Once we do the checks with the last digit, we can chop that last digit off using integer division by 10. And since we are using this while loop, this entire code segment will repeat from right to left of the number. So the main difference between this method of doing the problem and this method of doing the problem is that in the first method, we are taking a string version of the number and going through each of the digits from left to right, 128, 100, 64. And in this method, solution 2, we are going from right to left, since we are chopping up the last digit and then looking at the next digit, that's the last digit, and so on. We'd be going from 4, 6, 8 to 1, 0, 0, 1, and so on. Our next problem is called test grader. You have to write a function that takes in two parameters, a list of student answers, and an answer key list. The function should return the grade that the student scored on the test. So we'd have to check. We'd have to loop through both of these and write code that would check how many the student got correct. Now would be a good time to pause the video, and if you're not sure, we'll go over a hint of how to solve this problem. Alright, so a hint for solving this problem is to write out the approach like this. When we have complex problems like these with a lot of things going on, it's a good idea to break it down into a plan. Our plan doesn't need to have the correct syntax, just the techniques we're going to use to approach the problem. First thing we're going to need to do is to create a variable for the number of correct answers. We're going to track this throughout our algorithm. Once we have that, we need to use a for loop to loop through each item in the student answers list and the answer key list. While we are looping, we're going to be making some comparisons. If the answers at the index of the student list of answers is equal to the answer key list, we'd have to increment the answer correct variable by 1 because that means that the student got the correct answer. Once we are done with this for loop, we have to calculate and return the percentage grade that the student scored on the test based on the number of correct answers and based on the total questions that were asked, which we can get using the length of the list. So here is the solution for the test grader problem. In our function definition line, we called it grade test, and we're taking in two parameters, student answers and an answer key. Both of these are lists. We start out by creating our variable numCorrect and initializing it to have a value of 0. We will update this in our loop every time the student's answer is correct. We can create a variable called total questions and assign to it the length of the answer key. This will be useful in our loop and in our calculations later on. Our next step is to loop through each item in both of the lists. Since we know that usually we have a length of one of the lists, and that's already stored in a different variable, we could just use that variable inside our range function here. For I in a range, that's how we make our for loops, we're going to be doing the comparisons between the student's answers and the answer key's answers. If the student answers at the current index is equal to the answer key answer at the current index, we know that the student just got a correct answer. In that case, we'd increment numCorrect by 1, using this plus equals 1. We keep doing this and we loop through the entirety of both of the lists. And once we're done, we have to calculate and return the percentage grade. So the percentage grade would be 100 times numCorrect divided by total questions. So why do we do 100 times? Let's take a look at what happens if we do just numCorrect divided by total questions. For example, let's say we got a 1 out of 2. That would just be a 0.5. But we know if we got 1 out of 2, that's equal to 50%. So if we go from decimal to percent, we need to multiply by 100. So this division problem would give us a decimal answer, and in order to convert to percent, it's remember to multiply by 100. That's what the question asks us to do, return the percentage grade. So once we're done writing our function, always a good idea to test it. So you make a student test that will have the results of the answers that the student wrote, and a test key that will be the actual correct answers for the test. We're going to print the function call and put in the correct parameters, the student test, and the test key. So let's just do the math for this one and see what the correct percentage should be. The student got this one right, this one right, this one right, and this one right. So that's 4 correct. 1, 2, 3, 4, out of a total of 1, 2, 3, 4, 5, 6. 4 divided by 6 simplifies to 2 divided by 3, which turns out to be 66.6 repeating percent, and that is what is printed by the function, so we know we did it correctly. Our last problem for the day is to write a guessing game. We're taking a break from functions, so we're just going to write a program directly now. We have to generate a random integer from 1 to 100. So this is a big hint to import the random module. Then we have to keep prompting the user to guess an integer from 1 to 100 until they guess it. Okay, The keep prompting part here sounds like we need to use a while loop. Also, the until is another hint that we need to use a while loop. And the prompting the user part means that we need to use the input function to get user input. After each guess, we have to tell the user if their guess is higher or lower than the actual number. This sounds like something we would do with if statements and less than or greater than signs. And the last part of the project, once the game is over, tell the user how many guesses it took them to guess the answer. This means we have to use a counter variable at the beginning and increment it after each guess. Based on this information, your job is to pause the video right now and write the guessing game program. That would be a good time to pause the video and resume when you're ready to review the solution. Okay, let's go over the solution. Our first step in the guessing game is to import random. We know that we need to generate a random number, and we can't do that without the random module. Once we've done that, we need to use the randint method with the parameters 1 and 100 to generate our mystery number. We will assign that value to a variable called mystery num, and we're going to use that later. We also need to count the number of guesses, so it would be a good idea to create a counter variable and initialize it to 0, because at the beginning of the game, the user has made 0 guesses so far. We're going to increment it every time the user makes a guess. Now comes the actual playing of the guessing game, which is all inside this while loop. We create our while true loop, which will continue to execute until we break out of it. And we would have to break out once a certain condition is met, and that certain condition is when the user guesses the correct number. So inside the while loop, we have to first prompt the user to enter a number from 1 to 100 using our input function, and we cast that entire result to an int, since making these comparisons with less than or greater than is something we would do with integers. Since they made a guess, we know that we can increment guess count by 1. Now comes the part where we actually compare their guess to the mystery number. If their guess is greater than the mystery number, that means their guess is too high, and we print that out to the console. Else if, or otherwise, if their guess is less than the mystery number, or mystery num, we print the guess is too low. Otherwise, we know there's only one case left. If it's not greater than and it's not less than, it's equal to. And if their guess is equal to the mystery num, we know that they guessed the number. So we print, you guessed the number, it took you however many tries. We use string concatenation with a plus. We use guess count, which has been storing the number of tries, or number of guesses. And we cast it to a string because it was originally an integer. And after that, we just put guesses. So it would print out as it took you a certain number of guesses. And since they guessed the number, we are done with the guessing game, and we can break out of the while true loop because we don't need any more guesses from the user. Let's take a look at an example when we run this code. First, let's take a look at the actual number, which is 91. We will make sure that the computer correctly responds to our guesses. If we guess 50, our output is too low. That is correct. 50 is less than 91. Then we're going to guess 75. This guess is also too low. This is correct. 75 is less than 91. Now we're going to guess 88. This guess is also too low. Well, 88 is less than 91. That's correct. Now we're going to guess 96. 96 is actually greater than 91, so our guess is too high. Once again, that's correct. We lower it to 92 is too high, 90 too low. So that means that we know it's between 92 and 90, which gives us 91. The approach that we used in this guessing game example here is kind of like a binary type of way of breaking up the problem. We are halving the possible number of possible range of numbers we can guess every single time by going halfway between the valid range each time. And at the end, we get the correct message, you guessed the number, and it took you 7 guesses. Let's just double check to make sure that it actually took us 7 guesses. 1, 2, 3, 4, 5, 6, 7. Yep, this program works correctly. Now let's go over the exercises for the week. The first one is to write a function that takes 2 parameters and returns whether or not the 2 parameters are anagrams. So what is an anagram? An anagram is simply a word formed by rearranging the letters of another word. So example, listen and silent are anagrams because they both have an L, an I, an S, a T, a E, and an N. And they have the same number of each of these, just one of each. And what our program should do is it's writing a function and return true if the 2 words that are the parameters are anagrams, and otherwise it should return false. So there are 2 possible approaches for this one. We're going to go over both of them. One involves making a histogram for the letters and checking if the histograms are equal. Another one is a bit more simple and it involves sorted. Let's go over the first solution with dictionaries. In our function definition line, we call the function R anagrams, and it takes in 2 parameters, word 1 and word 2. We make a dictionary histogram for both of these. If you need a refresher on how to do that or why a dictionary histogram works, you can go back to the lesson on dictionaries. Once we have our dictionaries for each of the words, we're going to return if the dictionaries are equal, because if the dictionaries are equal, this Boolean condition will return true, otherwise it will return false. If the dictionaries are equal, that means we have the same number of each of the letters, which means that the 2 words are anagrams, and otherwise, if this returns false, that means we don't and that they are not anagrams. Once again, always a good idea to test our code. We're going to do it here again. We're going to print the function call on silent and listen. We know that was our example, so that has to be true. For this one, the next one, Nagram and Anagram. They have the same letters, but Nagram has 2 spaces here, which would make it have a completely new character. Space, don't really match up with this one because there's no spaces in this anagram. So the other way to do this is simpler, but doesn't always make too much sense. But once you understand it, it will become a bit more easier to use in the future. So in this one, we use the sorted method. We check if both words sorted lists are equal. So the sorted list of each word would just be all of its letters in alphabetical order. So if they consist of the same letters, then the lists will be equal and they will be confirmed as anagrams. Otherwise, we'll get an output of false. When we run the test code, we get the same results as before, and we know that it's correct. Okay, let's go back to the second exercise. Exercise 2, no duplicates. You have to write a function that takes in 1 parameter, a list, and it returns the list such that it is sorted and contains no duplicates. Alright, now would be a good time to pause while we get to the solution. Okay, let's take a look at our solution. We have an input list because we want to remove duplicates from a list and sort it. So that's what we're going to call our parameter here. We called our function name no repeats. Fine, no duplicates, no repeats, close enough. Inside our function, we're going to create a result list. This is the list that we want to return that's going to contain the values from this list without duplicates, and it's also in a sorted manner. Now what we're going to do is loop through each item in our input list. If the item in the result list, if the item is already in the result list, that's what this condition is checking here, this Boolean. If the current item is already in the result list, that means we don't want to add it again because then that would be a duplicate. In that case, we just continue, which means we skip everything in the for loop after this part, which would just be appending the item to the list, and we go to the next iteration. So let's say we had an item 1. We'd go through this. The first time around, it's not in the list because the list is empty. So we don't continue, and we actually append it. Result list, and we append the current item, so it now has 1. But the next time we go around and we see a 1, the item is in the result list, so we continue, which means we skip this part, and then just move on to the next number, which is 2. Once we are done with this for loop, the for loop starts at here and ends at here. Once again, very important to look at the indentation. We have to return a sorted version of this list, so we just take the result list that we're creating with this for loop and just return a sorted version of that. We can test our code with a sample list, no repeats. Then our list will have 1, 2, 4, 12, 5, 1, 2, 4. 1, 2, 4 are repeats, so they should not be included twice in the list. And we see that they're not included twice in the list. There's only one occurrence. And this is also in increasing numerical order, so it is sorted as well. The last thing we're going to do today is a challenge exercise. If you want a challenge, you can keep watching. Otherwise, the main points of the lesson have already been covered today. The last exercise is a challenge exercise. We have to write Hangman game. Let's go over the basic format of the game. We have to ask the user for a word. Then we have to prompt the other user to guess letters in this word. If the letter that they guess is not in the word, we have to update their number of lives. We have to display the word with underscores and letters based on the guessed letters. So if you're not sure what exactly Hangman is, now would be a good time to just pause the video, maybe just look up how exactly to play Hangman. You can come back ready to learn how to code it yourself. So for example, if we had a word, Mississippi, and I guessed S, my output should have blank blank SSI SS. No, let's do that again. Sorry. Blank blank SS blank SS blank 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 blank, because I guessed all the S's, but I haven't guessed any of the other letters. Okay. Let's go over the approach for doing this. Every time we have a big program that we have to write, we have to go over how to approach it. The first step is to store the user input for the word in a variable, because one user is going to tell us what the other user has to guess. So we're going to store that word in a variable. We're going to print a bunch of new lines so the other player cannot see the word that they have to guess, because that would just be too easy then. Yes, I know we can just scroll up and see, but still, this is better than nothing. Our next step is to make a list of the letters in the word using a for loop, and it's easier to manage lists and change them up because they're mutable. They can be changed. If you have a string, it's kind of tough to do because we can't change them around. And what we're going to do in this approach, there's many ways to solve this problem or code this game. This is just one way to do it. We're going to create another list that is only underscores and is the same as the length of the list of letters. After that, we have to create a lives variable and initialize it something. So this is the process for beginning our program. We're going to have to start off with all these initial variables. Now, what we have to do is actually develop a logical format for playing the game. What we're going to do is have a while true loop. And once again, not all of this is exact code. It's just pseudocode, which is just a plan for writing code. We're going to have to continuously ask the user to guess the letter and store it to a variable. We have to check if that letter that they guessed is in the word list, which is storing all the letters. We have to traverse the word list and spaces at the same time, and everywhere, every position where that letter appears in a word list, we have to change that space we have to change the underscores to the letter in the list. Once again, after that, we have to print each item in the underscore list, which would kind of be what we see here. We'd have to print this output part out after each guess so the user sees the progress that they've made. And if we're at the point that the user made a successful guess and there's no more underscores in the list, which means that they guessed the entire word, we just have to break out of the loop because we are done. Otherwise, if the user guesses a letter that's not even in the word, we'd have to decrement lives by 1, subtract 1 from lives, display the remaining lives, and in the case that they have no more lives, we'd have to print you lose. We have to reveal the word and break out of the loop because still the game is over. So now let's go over the solution for this one. This one's not very easy to fit on a Google slide, so we will just go over it directly in REPL. First thing we do is ask the user for the word using our input. We're going to store that to a variable called word. Next thing we have to do is print a bunch of new lines so that the person who has to guess the word can't just see the word. Next part, we are making a word list to make a list version of this word. For example, if we had the word banana, the first item would be the string B, then the string A, and the string N, and so on. Because it's easier to work with lists since they are mutable. Now, we're going to create a spaces list. Starts off as empty, and based on the number of letters in the word that the player made, we're just going to add an underscore to this. So an underscore we use because, going back to our presentation, our output has Mississippi. You see these underscores here, and that's the general format we're going to be using. And if you want to print this list out, we want to make it look nice. We don't want the curly brace, not the curly braces, the square brackets and the commas in between. We want it to be just the underscores and a space in between. So we write a loop to do that for us here. I'm going to run the program and show how the beginning part works. Let's stop it and let's run it again. Enter a word for the other player to guess. That's what's going on here. Let's say I want them to guess banana. So now, if we just narrow this down, creates all these spaces depending on how far you're zoomed in. This should be enough so that the player can see the word, but if not, we could just add more new lines here to fix that. We have made our word list, we have made our spaces list, and we've also printed our spaces list in a nice format, and you can see it has enough for all of the letters in banana, B-A-N-A-N-A. Now we have our lives variable setting it equal to 7, and from line 25 we are implementing this solution that we have here into actual Python code. Continue to loop until we meet one of the conditions where either the user wins the game or they lose the game. You have to ask them to guess a letter. So it's asking you to guess a letter. Let's guess something that's actually in the word. So A. Now what we're doing is checking if this guess letter A is in the word list. Well, a word list is just a list representation of the original string of banana. And A is definitely in there. So this evaluates to true and we go through this process. We loop through the word and we change the spaces list based on where this A appears in the word to the actual letter. The next part is to go through the output again. We have to print this out once again. We have just made this into a list version of what this looks like. And since we want it to actually print out, we have to write this for loop again, which is what we did up here. Now we have to check if there are no more blanks or underscores. Let's say the user guessed the word. If there's no more underscores in this spaces list, that means they're done. But so far, we see that there clearly are underscores in this printed representation of the list. So clearly we're not done. We have to keep going. Now this else lines up with this guess letter in the word list. Else is if I get it wrong. Well, there's nothing here, so what do I do next? We have to remember, this is a while loop, so we go back up to the top, and it's going to ask us for a letter. So let's say I do something like Y. Now in this case, it would check, is the guess letter in the word list? And it's not, so we have to take 1 away from lives. Lives was initially 7. It's only 6 now. Then we print that Y is not in the word. So you can see here, guess letter is storing the letter we guessed. Then we print lives remaining. Since lives is an integer, we have to cast it to a string and do a bit of concatenation. We also check if we have 0 lives remaining. Then we have to print no more lives, and then we have to tell them what the word was. We also break out of the while loop because that means that the person lost. So now we can enter something else. Let's do a case. Let's say we win the game. Say we type in B, we enter N. In this case, what happened is we got to this point, and this condition happened to be true. There are no more underscores in spaces, and we print, congratulations, you guessed the word, and we are done, so we break out of the loop. After the while loop, we just have this message that says press run to play again. We're going to play again, and let's do it in a case, let's say we lose. Let's say we do apple this time. Let's say we just do A, B, C, D, E, F, G, H, I. Now we get no more lives, the word was apple, press run to play again. So we see that this hangman program works as we wanted it to. It's pretty basic. So if you want to give yourself a challenge to this challenge and make it more complex, here are a couple of things you could try out. Try to work with user input. Try to handle invalid input. For example, if the user enters symbols or numbers, or even find out how to handle uppercase letters. Try to use dot lower to fix those. You could set a limit for word length to make the game reasonable to play. You could also handle invalid guesses, not just invalid words. Anything besides a single letter is just invalid. And you can also add an option to play again after the game is over. There's a lot of things you could do with just this starter code. You can keep going and make your hangman program as interesting and complex as you want to. I'll go back to the presentation. And that is it for this week's Codivate Python class. Have a nice day and hope to see you in the next class.